So this is called humoral or B-cell immunity. Okay. So what is the evolution of B cells? You have stem cells in the bone marrow. This bone marrow is where B cells are derived. Remember, all cells of the blood start in the bone marrow. Okay? So B cells that are produced in the bone marrow they mature there. Okay? That makes sense? So think of it this way. You are born in Cleveland and you attend Cleveland State. You don't go anywhere from your hometown. Does that make sense? So what happens during maturation? So-called negative selection. So, just telling you that B cells essentially can recognize antigens. Am I clear? Now remember I asked you a question like 15 minutes ago. Can a human protein be an antigen? Now what would you say? Yes. Should it be perceived as an antigen by your immune system? No. Right? So it can be, but your immune system should not recognize it as a true antigen because it shouldn't look for it. Does that make sense? So what happens during negative selection? Inevitably, some of the original B cells that are produced in the bone marrow, they will be what's called self-reactive. They will be activated by your own proteins. Does that make sense? So these self-reactive cells undergo apoptosis. Is that clear? Good? Now, once you got all the bad seeds out, ideally, all the self-reactive cells are dead, you can send the mature B cells to the lymphoid tissue. Okay? Lymphoid tissue implies draining lymph nodes, like axillary and cervical lymph nodes and inguinal lymph nodes, and spleen. So far we good? In lymphoid tissue, eventually, after the infection, they expose to antigen. Okay? Does that make sense?
So after the infection in the lymph
So
tissue.
here's the thing. Okay. Let me, not even an infection. I go to get my COVID vaccine. I get injection in my shoulder, right? What is the closest draining lymph node? Left axillary, well, it's a set of left axillary lymph nodes, right? So this antigen eventually, well, mostly through the local blood flow, will end up in the axillary lymph nodes. And B cells that are there will be activated by this antigen. Does that make sense? Did I answer your question, Julian? Yes. So, once they get activated, they undergo differentiation and proliferation. Differentiation means that cells become more specialized. Are we clear? Proliferation means that they become more numerous. This is why, for instance, in some patients who received COVID vaccine, swelling of the lymph nodes was reported. Yeah, no shit. you know, they grow, there's a lot of them, and what they differentiate into. They differentiate into, I'm skipping one of the steps, plasma cells and memory B cells. So plasma cells produce antibodies. Memory B cells, they keep immunological memory about the antigen. Does that make sense to you? You good so far? I'm going to try to leave it here, but there's something I wanted to mention. Make sense? Everybody remembers antibodies that we were just talking about. So how these B cells actually get activated? I'm still going to be using black, just it's convenient. So imagine you have three different populations of B cells. One population has a surface receptor, which is essentially an antibody tethered into the membrane, like this. It's clone number 1. Another has like this, and another has the receptor like this. So each of these pictures represents an individual clone of B cells. Does that make sense to you? What is the clone in this context? Clone means that all cells in this population carry this receptor. All cells in this population carry this receptor with that specificity. Okay? Now the antigen is coming. Which clone will recognize the antigen? Third, yes. So this is called clonal selection. The recognition of the antigen with the proper B cell clone. And what's going to happen to that clone? Proliferation and differentiation, right? So now we have many cells like this. So this process is called clonal expansion. And what these cells are going to produce? They're going to produce antibodies with this specificity. Does that make sense? Good? Now, one of the features of B cells is that they can, it's important, they can, many of them can recognize an antigen directly. They don't need any help. Some of them do, but some of them don't. And that's important. They can't recognize an antigen directly. Are we good so far? We good? Questions here? So, I'm trying to think. Yeah, got it. So, clonal selection and expansion. You've got plasma cells that produce antibodies. You've got memory B cells. Now, one topic I'm going to skip in terms of writing. There are 5 types of antibodies. Listen, there are 5 types of antibodies. They all are summarized in the table, in the notes. IgD, IgE, IgA, M, and G. Please, don't know the numbers. Any numbers are relevant. I'm going to summarize what you need to know. And it's written there. IgD. That's the B cell receptor. IgE, responsible for allergy. IgA, mucosal responses. Now, for IgA, it's also useful to remember. It's not only mucosal responses. So, for instance, if anyone had COVID here, then you have IgA against coronavirus, most likely, in your respiratory mucosa, okay? It's also a dimer, and it is present in the breast milk. So this is how newborns get their passive immunity. We good so far? IgM is the primary responder, the antibody that's produced first. And IgG is the most common antibody, the most abundant. It's produced second. It can cross placenta. Both IgM and IgG can activate complement. Now, while you are writing this down, I'm going to draw a little graph, and I will explain the primary and the secondary response, because I think it's really important. I don't know if you are working directly with patients now, but you will in the future, and you should be able to explain them why the hell the vaccines work. Okay? So imagine that this, and I'm not gonna invent, a bicycle or invent the wheel one more time. It's gonna be your vaccination, all right? So here you receive your first shot. Imagine you never had COVID, so you receive your first shot, right? About a week later, you're gonna develop a response from IgMs and IgGs. And yes, they both are going to subside. So does that mean that you're not protected? No, it means that the original production of antibodies went down as it's supposed to, but your memory B cells are already formed, okay? And here, you get your second shot. Do you have some IgM production? Yeah. A bit. Look what happens to IgGs. This is the boost. Does that mean,
That's why you feel terrible after this.
That's a different story. Why you feel terrible? The short answer, nobody knows. When somebody asked me what side effect I had after my both shots, I said 5 miles run. So I know people that felt terrible. I know people who felt nothing. Basically, yeah, you activate your immune system. There may be some inflammation. There may be some immune responses that trigger that malaise. Fine. You're going to suffer for a day or two. Okay? It's better than potentially die. Okay? So, does that make sense, that idea? This is the boost. The common question. What about the third and the fourth? General knowledge in immunology, it does give you a little bit of a boost, but not as much as the second one. Again, it depends from vaccine to vaccine. If you look at your childhood immunizations, you get, I don't know, polio shot like every 3-4 years or something like that. Because, yeah, it kind of disappears with time. It's okay. This happens. Does that make sense? And there was a study recently in England, published study, that demonstrated that people who had COVID, after the first shot with mRNA vaccine, their antibody responses are basically the same as in people who never got sick and received a full dose. But interestingly, the infection itself does not necessarily result in the production of robust levels of antibodies or memory B cells. You see what I'm saying? So vaccine is superior to infection. And it's not the first time we see it. It's for HPV, it's the same story. Okay? For hepatitis B, it's the same story. We good so far? Now, told you about the types of antibodies. Now, mechanisms. What antibodies, what can they do? I have a pretty nice illustration in the notes. I'm going to quickly highlight the most important features. So, Neutralization is usually for viruses. Antibodies bind to the virus, and virus can't do anything. Okay, think of it as a quarterback that's surrounded by, like, I don't know, 3 linebackers and 2 quarterbacks. Agglutination, very effective way against the bacteria. Precipitation works great with toxins. When you get bitten by a venomous snake and you receive antivenin, what you essentially receive is antibodies to the venom molecules. They bind venom and that's it, nothing happens, okay? Complement activation. You know the outcomes, that's a classic pathway. Now, one important feature that I always kind of focus your attention on: antibodies kill opsonize. Now remember opsonization that we were talking about when you have pathogen. Okay. Now pathogen is now surrounded by a bunch of antibodies. And what's the point? It's to make it more attractive to your immune system, to macrophages. Does that make sense? So at the end of the day, it's really nice. Look, this is a really nice connection between 2 systems. Check this out. First, you have specific humoral immunity here that via complement activation connects to innate immunity. You see that? That makes sense? And antibodies serve as a condiment for your bland pathogen. They essentially make it more attractive for macrophages. So again, a link between adaptive humoral immunity and macrophages as a part of innate response. Are we good so far? Now, last couple of bits here. First, types of immunity. Active versus passive, and natural versus artificial. This is super simple. Just have to be able to recognize. So look, you get infected. Let's use coronavirus, okay? You get infected with coronavirus. Does your immune system see an antigen of coronavirus if you get infected with coronavirus? Yeah, of course. You get a coronavirus. So this is active immunity. Is it a natural route? Yes. So infection is natural active immunity. You get a vaccine. Does your immune system see an antigen? Absolutely. But is it natural? So artificial active. Someone elderly goes into the hospital and receives antibodies to, like someone immunocompromised who can't produce a response to vaccine, they get antibodies. Do they see the antigen? Not yet, so passive, right? And artificial, because they receive. A child gets antibodies from mom with a breast milk, natural passive immunity. Match the description to the terms. Does that make sense? Good? Okay. Oh, last little bit. Why it's called humoral. There's nothing funny about it. Humor from Greek is liquid, fluid. Antibodies end up in the plasma, in the fluid component. Basically, what it tells you, and sometimes it works. You probably have heard about convalescent plasma studies. When you take plasma, specifically plasma, from people who recovered from COVID, and transfer them to other people, basically, right? And that should protect. It's a bit more complicated because the treatment was originally approved for folks who already ended up in the hospital. And by that time, it's just too late. It's too late, okay? And another problem, I listened to an interview with a guy who was actively pushing for this from Johns Hopkins. He said that it makes sense to do the plasma transfers locally. Because of small variance between viruses, if you take plasma from Cleveland and try to use it in California, it's probably not going to work. But if you use plasma from a person who lives here to treat a person who lives here, it's likely going to work. That makes sense?